All right, so our final piece, our final section of chapter 3, I'm going to start right off with reaction yields. We're picking up from stoichiometry and then limiting reagent. And so we just looked at how to solve reagent problems, limiting reagent problems. Next, we want to look at yield. So in many experiments, the amount of product is less than expected, right? So losses can always occur for different reasons. Could be mechanical issues. We'll probably see that when we make our aspirin. It's going to stick to the glassware. It's a little hard to get everything out. If you're dealing with volatile or low boiling products, there could be evaporation. Some solid will always remain in solution. Right? There's also competing reactions, especially in organic. A lot of times, as an organic synthetic chemist, 70 and 80% is usually a really good percent. Right? There could always be some competing reactions going on there, some side reactions. All right, so the main reaction, for instance, could be 2 phosphorus with 3 chlorides going to PCl3. A competing reaction for that would be PCl5, which is a byproduct. So after we've made the PCl3, some of the chlorine gas will continue to react with that and form the PCl5. So again, you could have competing reactions or multiple step reactions where you need it to stop before it goes on to step 2, but it will rearrange. So what we look at are yields then. Theoretical yields versus actual yields. So actual yields, that probably makes sense, right? It's what you have in hand, how much you actually made. Your theoretical yield is the amount of product that must be obtained if no losses occur. That's basically what we've been doing with stoichiometry. So we'll take the limiting reagent and we'll say if all of this goes to complete reaction, this is the amount of product we should be able to have, right? So this is the amount of product if all of the limiting reagent is consumed. Your actual yield is the amount of product that you've actually isolated at the end of the reaction. So this is what you actually obtain experimentally, physically, right? Now, how much is obtained in mass, units, or in moles? So we can do percent yield in either mass or moles. Typically, in reports, you're going to see it in mass. Now, percent yield is looking at the differences in those. So we're going to calculate our percent yield. It relates the actual yield to the theoretical yield. So your basic calculation is this: percent yield is equal to the actual yield divided by the theoretical yield times 100%. So if a cookie recipe predicts a yield of 36 cookies and yet only 24 are obtained, what is your percent yield? You'll take 24 divided by 36 times 167%. And that's what a lot of chemists will talk about when we're looking at synthesis. Right? What is your percent yield? What's your bang for your buck? Now, percent yield calculations will be hidden inside of stoichiometry problems. When 18.1 grams of ammonia and 90.4 grams of copper oxide are reacted, we've seen this reaction before, the theoretical yield is 72.2 grams copper. Now we calculated that back in segment 4. So if you want to go back and take a look at that, you can see how we did that calculation. The actual yield is 58.3 grams. What is your percent yield? So for percent yield then, we would take the 58 grams, divide by the 72 times 100%, and that means we have an 80.7% yield. Okay. So a chemist set up a synthesis of solid phosphorus trichloride by mixing 12 grams of solid phosphorus with 35 grams of chlorine gas and obtained 42.4 grams of solid. Calculate the percent yield of this compound. So again, notice it's kind of buried, right? The stoichiometry is kind of buried. We got to flush that out, do the stoichiometry to get the actual yield, or I shouldn't say the actual, to get the theoretical yield, then compare it to the actual yield. So the first thing we're going to need is our balanced chemical equation. So hopefully we know our naming. We got phosphorus trichloride. We're going to make it from phosphorus and chlorine gas. So we're going to have P plus Cl2 goes to PCl3. Now we need to balance that though, right? So we have to determine the reagent, the limiting reagent, determine the theoretical yield, and then calculate the percent yield. So it's a lot of steps into solving these problems. So we can get our molar masses from our periodic table. We know the relationship for our moles. Now we want to determine the limiting reagent. So we have 12.0 grams of phosphorus, right? We're going to get rid of grams of phosphorus, get into moles of phosphorus, get out of moles of phosphorus to moles of chlorine to grams of chlorine, 41.2 grams of chlorine. So for the 12 grams of phosphorus, it's going to be 41.2 grams of chlorine, but we only have 35. So at this point, we know the chlorine is the limiting reagent. All right. So to determine the theoretical yield then, we'll start off with chlorine as the reagent. We'll go to 1 mole of chlorine. We know that from the balanced equation, it's going to be 2 to 3. And then we're going to multiply that by the mass of the PCl3, which means we should make 45.2 grams. Now I want to determine the percent yield by looking at our actual yield as 42.4, and then our theoretical yield was 45. When we run that through, we get 93.8%. So our percent yield then was 93.8. So if you need to back that up, all right, the first thing we did was we used our determining reactant. We figured out which one was going to be the limiting reagent. That was from segment 4. Once we knew the limiting reagent, we determined the yield. This was the stoichiometry we did in segment 4. Okay, so we figured out how many grams of PCl3 we should make. And now the new piece is this last piece, determining the percent yield. Here we're going to take the actual yield, divide by the theoretical yield we just calculated, multiplied by 100%. All right, so when 6.40 grams of methanol was mixed with 10.2 grams of oxygen ignited, 6.12 grams of CO2 was obtained. What was the percent yield of CO2? All right, so there are your options. You've got some molar masses there. Go ahead and pause it and work this out. So hopefully you came up with E, 69.6%. So we're going to start with the 6.4 grams of methanol. We're going to convert that to oxygen, right, through our 3-step process. We'll get rid of grams of methanol. From the periodic table, we'll convert to moles. Using the balance equation, we'll get moles of CO2. And then from moles of CO2, using the periodic table, we'll get mass of CO2. So 9.59 grams of O2 would be needed. All right, so we need 9.59 grams of O2, but we have 10 grams. That means the methanol will be our limiting reagent. So the methanol then will be converted to CO2 this time. Go through the same 3 steps, but now we're going to CO2, and that tells us we should have 8.79 grams of CO2 in theory, right? That's if everything went perfect. However, we obtained 6.12 grams. So now we're going to take 6.12, divide by that 8.79, and that's how we got 69.6. All right. Hopefully you're making short work of that. A nice little easy step to finish off the segment. All right. So your summary here for stoichiometry. Remember, we can go grams of a substance to moles. So we're going to go from grams to moles using the molar mass. We can go to Avogadro's number and figure out how many pieces are there. Or for moles of A, we can use the formula or a balanced chemical equation, either or, and get moles of B. For moles of B, we could figure out the mass of B, or we could figure out the particles of B. Right? So hopefully you see the relationships here, and the little flow chart here will help you out quite a bit. Again, there's a moles calculation sheet under student resources. If you want, grab that. Make sure you have that when you're taking your exam. Right? That way you can see what you're supposed to do, how to get from mole to particle, how to get from mole to mass, how to get from mass to particle, particle to mass. Or print out one of these summary slides. This is a second summary slide that does a pretty good job of putting a flow chart together. Just have to remember where you're getting these molar masses. That's going to be the periodic table. Avogadro's number is 6.02, 2 times 10 to the 23rd. And then your formula, or you're going to use your balanced chemical equation to jump between A and B. All right, so again, the mole is the central piece. You need to be able to calculate those moles, and once you're in moles, you need to be able to manipulate moles to get to the other units, and it's all just different conversion factors. So with that, that finishes off chapter 3, and then we'll be moving on to chapter 4 next, looking at solutions and starting to predict products. So see you then.